start with the bigger picture first. With all these local interstellar clouds, including the one that the sun is traveling on, that's all fairly local. We're talking on the same scale of diameters as the double helix nebula. The double helix nebula is like 6 to 7 light years across. Notice that's the same scale, order of magnitude as the scale of filaments in here, like a matter of light years separation. But the local chimney is at the narrowest part of the pinch. It's something on the order of 1,000 light years in diameter. So that's the local chimney is this large hourglass-shaped tube with that ring of stars rotating around the narrowest point. So that's how we know it's a Z, like a pinch, and the sun is right down in there. But if you get that bigger picture first, and you realize that's a Bessel function filament, that gives you the background, like what we talk about in the local scale of our background magnetic field. What is that background magnetic field? That comes from the Bessel function of that larger scale thing. The background magnetic field for our solar system is the Bessel function magnetic field of that larger scale Birkeland current. And that's why when the mainstream, when they're sailing spacecraft right now outside of the solar system, they see a rotating magnetic field direction, and they try to explain it by, it's magnetic fields draping over our heliosphere. But no, if we are in a larger scale Birkeland current filament, then outside of the heliosphere, we should be able to detect that rotating magnetic field direction. And that's what they're detecting out there. Once the Voyager spacecraft got far enough out, they started seeing that changing magnetic field direction, which just proves that we're in an even larger scale Birkeland current. So the idea I was trying to get across is that our solar system is on a small scale. The local interstellar clouds follow a background magnetic field, but that comes from the even larger scale Birkeland current we're in. So I think we really have to get I'm hoping everybody can really get a picture of that, the local chimney, and see that the local chimney is a Birkeland current with a Bessel function field. If you get that, then you see where this local interstellar cloud, all that is doing is spiraling around the background magnetic field of that larger scale filament. And that's what's going to help really understand the idea of precession. Like what the ancient people knew is that precession wasn't around a single fixed axis, but at the end of our precessional cycle, according to the ancients, it didn't quite match up, and you get this serpent shape traced out by the North Pole. That's what the constellation Draco was supposed to be depicting, is that it's not just circling, it circles and drifts off over time. But that's because if our solar system is spiraling down a Birkeland current, but the background magnetic field that we're following is also circling on a greater scale, that's the path that the pole will follow. I mean, does any of that make sense, or am I going? I probably should have like at least crude videos of that.
It actually makes a lot of sense to me anyway. My initial idea of like further kind of development of this, well, first of all, I would like still to see how the outermost objects in the solar system move, but that's kind of a separate thing. I still haven't plotted them all. But anyway, the next thing to do, I thought, was to plot at least the directions and maybe, the inferred distances to the, like, at least, I don't know, maybe 50 or 100 nearest stars, and see where it leads to. But now from your words right now, I actually think that it may be more productive indeed to look at, you know, maybe these clouds that are like maybe 100 to 1,000 light years in size. So kind of disregard the stars at the moment and try to, you know, find papers or whatever that gives some, you know, coordinates, or I mean the vector of this local chimney tube or something like that. Maybe that would be, and that would be actually easier in the sense that, you know, to deal with 100 stars is harder than to deal with one cylinder or something like that. So maybe that's the way to go.
Yeah, and the one thing that jumps out on the scale of the local chimney, well, as you know, that every scale is going to present different features. Like a plasma a plasma discharge in the lab technically should do the same thing, where it neutral material is forced to the outside. But what you're not going to do in a laboratory discharge, or in like in a lightning bolt, you're not going to go out there and see that, oh yeah, there's a little bit of neutral material out at the outline of this. You know, that's ludicrous on that time scale and that size scale. But with the local chimney, this huge scale pinch, the outlines of it is what shows up. All that dense wall of neutral matter that's being ejected, that's what should happen in Markland convection. You see that in the local chimney. That was the feature that helped the mainstream map it out. They didn't know anything about what's going on inside, but the reason they see this hourglass-shaped object is they see neutral matter and dust out at the edges of this boundary. And inside it, that's where things get totally flipped around. They can't see the inside of it. That's where they're saying it's a hollow bubble. But we already know, that's all my arguments are, that all the evidence of plasma being really intense inside there show up in the bending of light, the Pleiades distance problem, the fact that there's all these hot blue stars down in the center of that pinch. That's a sign that there's current. But all the ways that we normally see charged particles, we don't see them in there, and that's why the mainstream thinks it's hollow. But that all makes sense is if that's a minimum energy configuration, if the local chimney is a minimum energy configuration filament, all that charge is going to be hidden to us. It's not going to, I know I'm repeating myself again, but these points are important. So if charge is following a magnetic field, you're not going to see cyclotron radiation from it, or, you know, you're not going to see if ions are sorted by Markland convection, you're not going to have one ion picking up an electron from another ion, because everything will already be sorted into that minimum energy configuration. So you lose recombination, you lose cyclotron. We've already talked about how the reversing magnetic field lines hide from Faraday rotation, so you don't even get an idea that there's current magnetic fields from current flow. So basically, when they say that local chimney is a hollowed out, sparse tube, they're exactly wrong. I mean, there's like a huge amount of charge, and especially, as you would expect, right down in that hourglass-shaped pinch. So we have to use all the EU ideas, pull everything out of how we see charge. Edward Dowday's ideas that plasma bends light, sure enough, it's there. The ideas of, like Wall Thornhill, that all this current should cause stars to be hot blue stars, that's there, and so on. I mean, it's all the evidence of that being a Z pinch with a lot of current is out there. And the mainstream, when they see that it's a hollow bubble, they're totally wrong. They're just absolutely wrong.
Well,
Like,
I was just going to say that it doesn't have to be. It doesn't have to be a pinch. It's just the star just has high current per meter, so to speak, on the surface.
Yeah, but the local chimney, where the Pleiades cluster is, that's all those hot blue stars. Yeah. They're right down in that hourglass-shaped pinch of the local chimney, and that was the puzzle that started me on it in the first place. It's like I saw the local chimney had that hourglass shape, and I was familiar with the mainstream description. They thought it was a hollowed-out bubble. Their idea is that stars coming down through the local chimney went supernova, and that shock waves blew out all the material, and that's why that hourglass shape. That's like a shock wave. It's a blast from all these stars in the middle on that stream going down the center. They just blew apart, and what we're seeing out there is a shock wave from that. But that's not right. That's the neutral material ejected by the filament. And they do see a stream going down through the center of blue stars. And even that, there's like so much data there. One mainstream observation you have to be aware of is that they find, whether they're looking at star streams or star clusters, there's a lot more correlation between the motion of the blue stars than the redder stars. So in other words, when you're mapping out a star stream, the blue stars seem to be all following in one path, and the red stars are all moving this way or that way.
But that actually makes perfect sense, because
if
the current will be enforcing uniformity along the currents where it's strongest and the pinch is strongest, or as you said, and the blue stars would be there. The ones on the side would be sort of ancillary, secondary induced currents and so forth.
And spiraling around, and that's the idea. Like if you look at if stars actually travel on helical paths, this is not what the mainstream view is, then all you would have to do is put the blue stars more at the center of the stream, traveling more axially, and then the red stars spiraling around more peripherally, where the current should be. It should taper off as you move out. That would make sense that they would be moving more helically one way or another. We'd pick that up in the red shifts. It'd be more random or more peculiar velocities for red stars than blue stars. But just that pattern, just to be aware of that pattern. I mean, forget my explanation of it. Just to know that there is a pattern to more random velocities of red stars than blue stars, and we know it's not just a misinterpretation of redshift as Doppler shift, because even in our neighborhood, the weird stars that we have to deal with, like Barnard star is a red star, Arcturus is a red star, and they're both known for really high proper motions that we can measure. I mean, we can measure them fairly accurately with parallax because they're close. And not only are they moving more randomly compared to us in the local standard of rest, but they're even moving weirdly compared to each other. They're not like two stars in the same stream. We've got these two red stars moving really crazily across our skies in different directions. That's something to deal with. That's something that, again, forget about my whole explanation for it. Just that's a good observation to have in the back of your head. And it works with clusters too, where they see you can identify a cluster more by the blue stars. They seem to be traveling together. You can tell what's bound to what, and the red stars are spiraling around all weird or have strange radial velocities and stuff like that. So that's okay. I'm sick of my own voice again.
Well, I can say that this is definitely a very interesting avenue of research, and I'm totally with you here. I mean, I really want to know what's going on in our environment. I mean, given all the weird things that I've already seen. So I have a couple of questions to you, if you if you don't
Yeah.
mind. So one of my questions is, I mean, as a person who is going to be deeply involved in all of this, what observational evidence would you look at to map, you know, this local chimney and things like that? Like, I mean, I so far, I mean, following your words today, I plan to start from this kind of scales, like 1,000 light years.
Yeah.
So what would you expect? Like, I mean, anything basically, it would help, because I have no idea where to find, you know, this data, how it's all oriented and things like that. So maybe I would have to, you know, construct it from scratch, basically.
Right. The idea is, if you look up the local chimney on the Sol Station site, is the best starting point. That's where you can get a good description of the hourglass shape and stuff. And separately on the same site, but on a separate page, which shouldn't be a separate page, they talk about that ring of, I'm probably going to mispronounce it, Gould's Belt or Gold's Belt. It's a ring of stars, and it's rotating right around the pinch, exactly what you would expect in the EU model. And that ring of stars, it doesn't
Like
make
those circles between the arms and legs of Squatterman.
Yeah, exactly. It's that teardrop, or it's the drop under the arms in the Squatterman shape. And the mainstream has at least three problems with it. One is that it does seem to be kind of bounded as a ring and rotating. It's also rotating in the wrong direction and the wrong plane. It's orthogonal to the chimney axis, which is what we would expect if it's but the mainstream is having trouble explaining why that inclination, why it's not rotating in the galactic plane. Why is it? If you look at the local chimney, you see it comes down at an angle through the galactic plane, and that Gould's belt is exactly at a right angle to the chimney axis. It's orthogonal to the chimney axis, right at the narrowest part. That's exactly where you would expect the torus. So that's, and what's interesting is that was picked out again by the hot blue stars in the group that were most seen rotating, not by any red stars. It's the blue stars around there they've got. But they also see a stream of stars traveling right down along the chimney axis. That's one of the Pleiades streams. And it all makes sense in the EU model. This is like a huge scale filament where individual stars are traveling along the Bessel function filament of that large thing. So you have a clump of hot blue stars right down in that pinch. That's the Pleiades. Then from there, that's where I stumbled on the Pleiades distance problem. Like, okay, I already knew the Pleiades is buried in this pinch, and now we're having trouble measuring the distance to it. And then when you look at the parallax, I think I should do a little video on that. I just think it's really important if everybody understands how direct parallax is done compared to relative parallax. Those were how the distance problems showed up. They each would skew in a different direction, and that's where the Hubble team did relative parallax and the Hipparchus team did direct parallax. And their answers differed in the way you would expect if there was light bending around the Pleiades. And you would think that the mainstream would have picked up on that idea because they know about the gravitational bending of light, and they know there's a lot of mass of stars there. But the problem is, and why it was rejected even as consideration by the mainstream, is that there's not enough gravitational mass at the Pleiades to cause that bending of light. Remember that even the amount at the surface of the sun is pretty small. So if you're talking about looking past stars, well away from those stars, there's not going to be any light bending in the mainstream model. But if that's really
I just want to go kind of with a small correction. You know, if you treat the gravitational lensing as like a regular lensing in a like geometrical optics, there is still like a special point on the optical axis, which is, well, like a focal point in optics, right? So for the sun, for example, such point of gravitational lensing focus would be at 55,000 AU from the sun. That's like, I don't know how much, maybe around 1 light year or something, or maybe half a light year, but of that order. But anyway, maybe, for the Pleiades, it's somewhere close to us, actually. That's what I thought. I mean, that's kind of a weird idea, but maybe there is, some special alignment that causes all these anomalies.
Yeah,
Who knows?
Well, if there is bending of light towards the center of like some filament, and the Pleiades clearly is in the center of this hourglass shaped, pinch. The most radical distance mismeasurements are going to be when we look at things at the center or things away from the center in the opposite direction. In other words, not up and down a filament. There should be no bending of light by a current filament if we're looking at any radius down a filament. If we continue looking straight down that radius, there should be no bending of light by any, charged double layers or anything like that. We should see consistent, except if we're merely grazing one, then we should expect radical differences, but that's like a whole nother topic, and I'll show you evidence that we do see that too. But here's one more point. Like if we're in a filament, and this is one thing the mainstream saw in magnetic field observation, is if you put yourself in a Bessel function filament and look radially inward, just say you're any random radius in a Bessel function filament, and you look inwards, what should you see? You should see a rotating magnetic field direction, right? It should point one direction down the filament, around the filament, and down the filament in the opposite direction. But if you look down along a current filament, you should see a consistent magnetic field direction the whole way. And it doesn't matter where you are. If you're out in a Bessel function filament where the field is axial, you should look all the way down the filament and still see that axial magnetic field. If you're out at a radius where the magnetic field is wrapped around the filament, but you look down the filament, you'll always see that magnetic field wrapped around. But here's what the mainstream actually found, is that if we look on two oppositely directed line of sights, we see consistent magnetic field directions that aren't there in any other line of sight. And that's exactly what they're giving you the axis. They're giving you the axial direction right there. You see that when we look across filaments in any other way, the mainstream arguments hold here too. What you should see is continually reversing magnetic field directions along any sight line. And that's in the mainstream data. They see magnetic field directions that reverse on continual distance scales, and they don't have the Bessel function model. So what do? They say it's magnetic turbulence. That's how they map it. But all the information is in their articles. When they say magnetic turbulence, once they start finding patterns, that's where you should tune in and say, well, we know what causes magnetic fields to reverse and follow these patterns. It's not because there's magnetic fields are being blown around, frozen into the plasma, and then blown around with the plasma. That's BS. We have a model that says magnetic fields should reverse on uniform distance scales on any sight line. So, man, I talk too much.
No, it's great. Yeah, really interesting.
If
But I still have many questions. But anyway, excuse me. To the last point. So you're saying that these, well, let's say, counter-rotating current layers are equidistant from each other. Is that correct? At large distances.
um, that's what the mainstream found, is that when they were looking at interstellar gas filamentary clouds, that's what always gets my attention. They saw magnetic turbulence that caused a reversal in in magnetic field direction on regular distance scale. So as they're looking across this filamentary gas cloud, I'll keep their nomenclature. When we look across a filamentary gas cloud, we see that the magnetic field reverses direction on regular distance scales, and they model that as magnetic turbulence. And
so like if we're seeing it from the side, so to speak, like on this picture, we're seeing like a field directed towards us, then away from us, then again towards us, then again from, I mean, as we move away from the axis. Is that correct?
Yeah, see, like this is where I started in the very beginning when I first came to EU. I thought I would use my knowledge of Faraday rotation. Like if if you look at that double helix nebula, if the magnetic field was really wound around it by the right-hand rule, then we should be able to look at background stars on one side of that filament and see a magnetic field pointed towards us. That's what Faraday rotation picks up, is line of sight magnetic field. So we should see a consistent magnetic field pointed towards us on one side of this filament and away from us on the other if there's a magnetic field wrapped around it. And what I realized before I had that Bessel function idea that Don Scott came out with is there really was no magnetic field like that, which meant then that there couldn't be any strong current through that. And that's what even put me off to the idea of, like, I was considering all these ideas that maybe they're not really current filaments. Maybe stars are charged locally, but this can't be current because there's no magnetic field wrapped around it by the right-hand rule. But now that's why when Don published his first paper, I knew that was the way out. If you understand Faraday rotation, the most important thing is that on any sight line, it's like the vector quantity of the magnetic field that matters. So if a magnetic field reverses on any sight line, it looks the same as no magnetic field. And that's where I realized Don Scott's model was the salvation in that. So like when you're looking across, now if we're looking, say, on one side of the double helix nebula, we should be looking through one radius where the magnetic field is pointed towards us, and then another one where it's pointed away and towards us and away.
Because there's layers.
Right. See, now when you see what they actually observe in current filaments in space, they see a magnetic field along the current filament. Well, that makes sense. If the current filament is a field-aligned current, it should be following the background magnetic field. So that makes sense that the filamentary cloud is following the background field. But the question I had is, well, where's the field of the filament itself? Where's this one wrapped around it? I see the background magnetic field only, but that's the beauty of it, because the background magnetic field obviously is the same across the whole filament. The field of the filament is the one that reverses direction and cancels out. So here's the kicker, that even if the background magnetic field is relatively weak, because it's the same across the diameter of the filament, that shows up in the Faraday rotation. But even if the filament itself had a strong magnetic field, because the component keeps reversing, it cancels out. So we'll actually see the background magnetic field of that a filament is flowing along, and the mainstream sees us. They see filamentary gas clouds aligned to and sometimes flowing along the background magnetic field direction. That makes perfect sense.
So I have a question just to clarify if I understood you correctly. So you're saying that the background field is directed along the axis of the filament, but the axis, like the magnetic field of the currents in the filament itself, that are directed kind of tangential to the axis around it, right?
Well,
in layers.
Right, but also axially, but back and forth, one direction and the other, around it azimuthally, but one direction or the other. But that's the part that cancels out because it keeps switching. But if a filament is following along a background magnetic field, that's the same everywhere, inside the filament, outside, across the radius of the filament. That component is always there, no matter what. And then the field of the filament itself, and that's what's fun to look at. Just look at Don's model and then try to imagine any sight line that gives you a field direction towards you is going to give you just a little farther a field direction away from you. Again, as I said, except if you're looking exactly down a filament, then whatever the magnetic field direction is going to stay the same all the way down that filament. As long as you look straight down at the same radius that you're at, you're always going to see that background magnetic.
That actually kind of, and I'm not sure if that piece of feedback would be appropriate, but who knows? So I had a kind of very vague feeling that this is sort of I don't know if you consider the universe as being conscious or something, or intelligent. So it's kind of a way of, dressing for these currents. So they kind of, wrap these magnetic fields around them so that nobody would, receive any, hard radiation or something from them. So they're like, we're just here doing our little stuff, going, along the background field. I mean, we're not bothering you with our, energetic particles, because we are dressed in our magnetic fields that are wrapping around, so you don't see anything.